So today we're going to look at the mean value theorem and how it relates to what we saw the other day with the Rolle's theorem. Ultimately, Rolle's theorem is a special case of the mean value theorem. Mean value theorem says that if you have a continuous function that on a closed interval, ab, and it's differentiable on the open interval, ab, then there exists at least one value in C where the derivative is equal to the secant line that uses points a and b. So the actual function here, this portion here, is the derivative at point C is equivalent to the secant line of the two endpoints for points A and B. So what that visually means is that if you have a graph, any curve, let's just say it goes like so, and we have our 2 points A and B, this point and this point here. If we were to draw a secant line, the mean value theorem tells us that there has to exist some point C where we can actually take this line with the exact same slope and find a point C where it has the exact same slope as the secant line. So, if you think about what we did with the Rolle's theorem last day, Rolle's theorem says that if you have this two starting and end points being the same, so they have the same y values, there's A and there's B. If you think about this one, the slope between these 2 points, the secant, because they're the same value, your slope is 0. And therefore there exists some point C where it has the same slope. So Rolle's theorem is a special case of the mean value theorem that just looks at it when you have two equivalent y values for the A and B starting point. Now last day as well, we also looked at finding where the minimums and the maximums occurred. So keeping this in mind, we're now going to look at what's referred to as monotonic. Function, if it's either increasing or decreasing one direction on a certain interval, then it's either going to be increasing or decreasing, and it's going to be referred to as being monotonic during that interval. When we look at the derivatives, not only now do we have the critical points, but now we can figure out whether or not the original function is increasing or decreasing based on the derivative sign. So if we were to look at the derivative of the function, if it's greater than 0, then the original function is going to be increasing on that interval. For when the derivative is less than 0, then the original function is going to be decreasing on that interval. Now if you think about it in terms again of looking at a function, here's our critical point. Let's call it C. It's the point where it's going to change. If we look at the slopes as we approach the critical point, they're all going to have the same sign. They're all going to be positive. Whereas when I look at the slopes on the other side of the critical point, we're going to see that all the slopes are going to be negative, and therefore that portion of the graph is going to have a decreasing slope to it. So by looking at the sign of the derivatives and the slopes of the derivatives, or slopes of the original I should say, we can see whether it's going to be increasing or decreasing. So let's consider this example to find out the critical points and where it's increasing and decreasing. First of all, you're going to need to find the derivative. So the derivative in this case is 3x squared minus 24x. Again, we want to find out where it's going to be equal to 0, so that way we can find the points where it changes direction. So if we factor this, then you can see we can take out a 3x, and you're left with x minus 8. This tells us we have a critical point at 0, and at 8, when this whole derivative is equal to 0. So now we're going to look at it in terms of a number line. We have some critical points. We have 0 as a critical point, and 8 is a critical point. And we have intervals that lie in between each of these. So either it's going to be a minimum or a maximum at one of these 2 points. What we need to look at now is the signs. We can choose any value lower than 0. Let's just say, I don't know, -1. And any value between 0 and 8. Let's choose 1. And anything larger than 8. Let's choose 9. If we plug this into the derivative, it tells us that if the derivative is going to be greater than or less than 0, it's either going to be increasing or decreasing on the original function. So we're still going to be using the derivative value here. If I plug in -1, you're going to have 3 times -1 times a -9. We actually don't have to evaluate, we just need the sign. Negative times a negative times positive, the whole thing is going to become a positive. If I was to plug in 1 minus 8, again 3 times a +1 times a negative value, that's going to give me a negative in that interval. If I plug in 9, and again you don't really have to evaluate it, 9 minus 8, the only thing we really want to look at is signs. Oops, sorry, that's all one bracket. There we go, and that's going to become a positive. Now it tells us now that our derivatives, for any value that's going to be -1 or lower, actually even the fractional amounts between 0 and -1, they're all going to have a positive slope. Here we have a negative slope between these two, that means it's going to be decreasing. And here we have a positive slope, which means it's going to be increasing. Now we can then consider what's going to happen at these critical points. At 0, we have something that is increasing and then decreasing on the other side, which means we're actually going to have a maximum. Here at 8, we're going to have something that's going to be decreasing and then increasing, so then we're going to have a minimum value. It is a cubic function, so we know it's going to have to go up, down, up. So we can do a rough sketch now based on 0 and 8. We don't know exactly the value of where the maximums are unless I actually plug 0 and 8 into it, but a rough sketch is that we know that it's going to be coming up. At 0 it's going to start heading down. At 8 it's going to start heading back up again. So to help us figure out what the graph's going to look like a little better, it actually would help us to evaluate at 0 and 8 in the original function to figure out where these vertexes are, the change in directions, the mins and the maximums. And here we've got our x value is equal to 0. And x is equal to 8. So what we've now got here is our derivative is going to be positive. This one's going to be negative. This is going to be positive. And if we actually evaluate when x is equal to 0, we're going to get 0. This one here is our critical point. This one here is our critical point. If I plug in 8 into this whole thing, we'd have 8 to the power of 3 minus 12 times 8 squared. We're going to be down at -256. So we would have something that's going to be increasing up to 0, 0, 0, 0, going all the way down, somewhere down here at -256, and then bouncing back up. So let's just say on my scale, there's my -256, approximately. Totally not to scale, but you get the idea. Here we have increasing from 0 this way. It's coming up with a positive direction. Between 0 and 8, we have our vertex here, vertex here. Here it is decreasing, and here it is increasing as we go this way. So here's what we can look at now if we're looking in terms of a table. If I was to give you a table where it gave you an increasing interval, a critical point, which in other words the derivative is actually equal to 0 at that point, another critical point where it's equal to 0, an increasing interval in between it, and a decreasing interval. So we can see on our graph how it can relate to these 2 points. Our x is at 1 and 4. Those are our two critical points. When we look at the region below 1, from negative infinity up to 1, it is decreasing. It's coming down at an angle. At 1, it's actually going to have a value of negative 10. So we actually have a point at this point here. At 4, we'd have a point up at 6. And we can see that we're going to be decreasing as we come down to negative 10. We're going to be increasing as we get to 4, and then decreasing from that point forward. So you're going to get a cubic in this case, something to this effect. Now what we're going to look at next day is looking at a change in direction where it goes from concave up to more of a concave down. So that's our next step that we need to look at, is some of these changing points where we're going from a difference of a curvature up to a curvature down.